Welcome back, folks. Last one here, going to be the shortest one out of all of them because we do not cover a lot with gas laws in this class. In fact, I'm lucky if I even get to it most semesters just due to the constraints of the time that we are together and the pace at which this course dictates. So we're going to do a little bit with gas laws today. Again, we're not going to spend a lot of time on it. This video is probably not going to be much longer than 30 minutes at the most, depending upon how slowly I work through some of the practice problems that are here. But that being said, this is the last part of 1030, so I hope you enjoyed the series. I thoroughly enjoyed it as well. You know, what's coming up next, hard to say, probably some AP chemistry stuff, but if you did like it, feel free to like, subscribe. I'm always looking to, give more people the gift of understanding chemistry. It's what I do for a living. It's what I love to do, and so I'm hoping that, you've enjoyed it, and if you have, then, I really do appreciate it. So, that being said, okay, I'm going to just click. There we go. Clicking the wrong button there. So what are our learning objectives for this particular video? Well, it's going to be relatively short. We're just going to learn different units for gas law variables, including amount, pressure, temperature, and volume. Use the combined gas law to explore relationships between variables of a gas. So we're going to learn a little bit about gas behavior and the variables that impact the behavior of that gas. We'll talk a little bit and discuss the ideal gas law, and then lastly use Dalton's law of partial pressures. There's so much more to gases than this, but for what we're trying to accomplish, this will take care of it. So, last couple of things that I want you to learn for this course is a little bit about gases and how gases behave, because gases are important in the medical field. Gases are used often. Oxygen tanks are used quite a bit, and there's lots of different gases that play a role in chemical reactions, so we want to make sure that we understand how the behavior of them works. So in order to understand this, we have to understand the variables of the gas that impact the behavior of the gas, and one of them is pressure. Pressure is just a measure of the force of something or the force of a chemical over a particular area. You can imagine, being stepped on by a person who weighs, 200 pounds on your foot. It's going to be a little bit painful, but a person who weighs half that much but is in a high heel hurts your foot even more because it's force over area. The smaller area of the high heel increases the pressure, resulting in probably more broken bones than if a heavy person stepped on your foot. Volume is in liters, just like what we've discussed previously. Amount is in moles. And temperature, believe it or not, temperature has to be in Kelvin. And we talked about how we convert between Celsius and Kelvin. You add 273 to that. We have to have an absolute temperature scale for this because we are going to be doing some math with these numbers, and we can't have negative values for temperature because that can lead to things like negative pressures, negative volumes, and we can't have those types of things. So we will always be dealing with temperature in Kelvin. Some standard units of pressure that you may or may not be familiar with, and again, that just depends on, I guess it just depends on where you get your pressure from, but most scientists will use ATM as their standard unit for pressure. 1 ATM is considered the standard pressure on Earth. That's an equivalent to 14.7 psi. You're probably familiar with that if you fill up your tires full of air. 760 millimeters of mercury, or 29.53 inches of mercury if you watch the Weather Channel. And if we look down below, we've got a variety of different units that deal with pressure. Pascal is one that's really commonly used in chemistry as well, but we're just going to try to keep it to the basics, at least for today. So the relationship between these variables is important to understand. So we're going to look at each set of variables individually and see what different factors impact each particular relationship here. So pressure and volume are inversely related to one another. That is, as one variable increases, the other decreases when the other variables of the gas are kept constant. So notice that when we have gas at a low pressure, the piston stays very, very high. But when we move the piston down and we decrease the volume, the pressure of that particular gas increases. You have more frequent collisions with the outside of the container. And so as a result of them being inversely related, the variables are multiplicative. So the pressure and volume, the product of those two things, in tank number 1 on the left-hand side is equal to the pressure and volume of the tank on the right-hand side. So what does this mean? Well, it means something very straightforward. It means we're going to be given 3 of these 4 variables. We just simply need to plug in and algebraically solve for the one we do not know. This relationship is very elegantly known as Boyle's law. So if you hear me refer to Boyle's law, you know we are talking about pressure and volume. So take a look at these pressures and volumes that are given here in this particular chart. So take a look at the very first one there on the left-hand side. That particular piston is under a pressure of 100 millimeters mercury and 8 liters. If we increase decrease the volume to 4 liters, the pressure increases to 200 millimeters of mercury. And if we decrease the volume to 2 liters, the pressure increases to 400 millimeters of mercury. But you notice when you multiply each of those pairs of numbers together, you end up with a total of 800. So again, that indicates that pressure and volume are inversely related. So multiplying them is the way to go when we're trying to solve some problems in regards to changes in pressure and volume. So we have a practice problem here. It's pretty straightforward. It says that the pressure of a gas has changed from 1 atm to 2 atm. What will the new volume be if the original volume is 32 milliliters? So you have the P1V1 equals P2V2. Think about what your initial pressure and initial volume are, and your second pressure and second volume are, and I will go through it with you here in just a moment. So as I mentioned before, we're going to be using Boyle's law here. The reason I know we're using Boyle's law is because we're dealing with the variables of pressure and volume. So that helps me understand a little bit more about what type of formula I'm going to be utilizing when I go through and solve for this. So pretty straightforward here. It's changed from 1 atm to 2 atm. So that's my initial pressure, and that's my second volume. And it says, what will the new volume be if the original volume, so original volume would be here. And all we do is plug in and solve. We don't have to change any of the units, provided that they are the same on both sides. Now that will change when we deal with what's called an ideal gas, but that's for another time and another place. So we just plug some numbers in here. So 1 atm, initial volume of 32. Equals our new pressure, 2 atm, and our new volume. That's what it wants to know. So we're just going to do a little bit of math here. So this ends up being 32 over 2 equals V2. So we end up with 16.0 milliliters for V2. And again, we can take a look at this relationship to figure out if we did it correctly. The pressure went up between P1 and P2. So that means that the volume should go down. And it did. So we know we've gone through and done this correctly. All right, let's look at a few more variables and do some more mathematical calculations. So the next relationship we're going to go ahead and dive into is what is known as Charles' law, and that is the relationship between temperature and volume. These are directly related variables. So what that means is that as one goes up, so does the other. Think about a hot air balloon. When you increase the temperature of the air that is inside of a balloon, the volume of that balloon expands and increases. So we can take a look at our information here. It's going to be a little bit different because they are directly related. We don't multiply them, we divide them. So the initial volume of a gas divided by the temperature is equal to the second volume over the second temperature when the gas changes. The temperature does need to be in Kelvin, so make sure you add 273 to the degrees Celsius. But if you look, we wouldn't multiply those to get those to be directly related to each other. We would divide them. You can see that 100 divided by 2, you could do 2 over 100. It works the same, but it's just a little bit easier this way. 100 over 2 is 50. As we increase the temperature, as we double the temperature, so does the volume. And we do that twice. We double the temperature, the volume doubles as well. So these are directly related. So the relationship is a little bit different than the relationship that we looked at previously. We still do math though. We get 3 variables. We plug in and solve for the fourth. So let's go through and determine the new volume of a gas originally at 25 degrees Celsius and 56.9 milliliters when the temperature is increased to 75 degrees Celsius, assuming the pressure does not change. So again, we're going to be using temperature and volume here. Look at the previous question. Look at the previous equation rather, and utilize that in order to be able to solve for this. Remember, temperature does need to be in Kelvin before you plug in and solve. We'll be back with it in here in just a moment. So again, I know I'm dealing with a volume and I'm dealing with a temperature, so I know I'm going to be using my formula. Let's put it off to the side here. V over T equals... I'm going to get a new stylus at some point in time. This one's got the rubber tip. One with the hard tip might make it a little bit easier to write some of this stuff out. That just looks like an angry face more than anything else. But regardless, we're trying to determine the new volume. So we're trying to determine V2. We have a gas originally with these variables. So we start off with 56.9 milliliters. Remember that does need to be in Kelvin. So we want to add 273 to that. So my temperature here, my initial temperature is going to be 298. Equals my second volume, which is unknown, and then my new temperature, which is 273 plus 75, which is 348, Now, lots of ways that you can algebraically solve for this. I'm a big fan of the cross multiply and then divide. So if you remember from math class, to cross multiply, we're just going to take 298 multiplied by x, 348 multiplied by 56.9, set them on both sides of the equals equation, and then solve. So we're going to end up with 298 times x on the right side, and 19800 on the left. We're going to divide both sides by 298 and see what we get for x here. So we're going to take that value divided by 298, and I end up with 66.4 as my new volume. Okay. And again, we can check our work here. The temperature increased, so the volume should also increase, which it did, which is good. All right. So we're going to continue moving forward, but again, just make sure you take a look at those variables, figure out what you're trying to solve for, and go from there. We'll be back soon. So we take all the variables from Boyle's law, Charles' law, and combine them together. We get it's called the combined gas law. So P1 times V1 over T1 equals P2 times V2 over T2. Now, given that you have 5 variables here, you could solve for the unknown that's one of them. Just again, remember, temperature must be in Kelvin, and the units of pressure and volume should be the same on both sides of the equation. I do want you to see that Boyle's law and Charles' law are both embedded into this. And if you notice in the equations, it's very specific. It says something along the lines of temperature does not change, or pressure does not change. So if we're dealing with Boyle's law and it talks about pressure and volume, but temperature not changing, if you eliminate pressure from that equation, you actually get Boyle's law. And the same would work with Charles' law as well if you were to eliminate the pressure aspect of it, assuming that it's the same on both sides. Now, if not, you're going to have to go through and do the math with all 5 of the variables, well, 6 variables, one of them being an unknown. So I've got an example here. It says a sample of nitrogen occupies a volume of 1.62 liters at 755 millimeters of mercury of pressure and a temperature of 0 degrees Celsius. What is the new volume in liters the sample will occupy at 725 millimeters of pressure and 50 degrees Celsius? So again, use the equation we just looked at previously. P1 times V1 over T1 equals P2 times V2 over T2. We'll do a little bit of algebra, we'll solve, and then we will go from there and see what this looks like. Be with you in just a moment. All right, so again, variable identification here, very important. So let's work through it one at a time. So we have an initial volume, so we'll call that V1. We have an initial pressure, we'll call that P1. And an initial temperature, we'll call that T1. The new volume is unknown, so that's V2. We have a secondary pressure, V2, and a secondary temperature, which is also V2. So simply put, we just plug these in and solve. Just don't forget that temperature needs to be in Kelvin. So make sure we do that when we set all this up. So we're going to start with the volume of 1.62, or V1. I guess P1 should really start this, so 755. Over 0 in Kelvin is 273. Equals, we want to know the new volume. We're given a new pressure, so 725 times x all over 50 in Kelvin, so 50 plus 273 is going to be 323 Kelvin. Okay. So now again, to solve for this, we're just going to cross multiply like what we just did. Like I said, there's a couple ways you can do this. I tend to prefer the cross multiplication method, just a little bit easier on my brain, something I've been doing for many, many years. So 197,925 times x on this side. Maybe a big number over here. And 395,061 on this side. So we're going to go through and divide these out. So 197,925, 197. And we should get our value for x. So again, just like I said, just plug in and solve. So take that value divided by 197,925. Essentially what I get is 2 liters. Now, a little bit hard to guess and check on this one, or that is check to see, okay, if this goes up, the other one goes down, or if this one goes down, the other one goes up, because you have multiple variables here that are changing. So the pressure is decreasing while the temperature is increasing. So it can be a little bit more challenging to figure out what's going to happen to the volume. Fortunately, both of these indicate that the volume rather should be increasing, but it isn't always going to happen that way. So it's hard to kind of figure out just by looking at it sometimes what's going to happen to the volume in and of itself. But again, if you go through and do the math, we should run into no problems at all. One of the most important gas laws that we experience is the ideal gas law. And if you notice that every time we've utilized the combined gas law, we have been doing it for conditions that change, right? Either the volumes changed or the pressures changed or the temperatures changed. Something has changed as a result of being able to go through and calculate the new volume, new pressure, new temperature, whatever. What we do now is we utilize the ideal gas law for variables that are constant. So you're going to find that there's not going to be two pressures, two volumes here. We're going to have one of each. And there's four variables that impact the behavior of a gas. It's moles, pressure, temperature, and volume. And the relationship between all these variables is expressed as PV over NT, which will equal a constant value, which we will call R. So to break this down a little bit more, I'll show you the formula in the form that I want you to utilize it, and then we'll plug some information in. But this constant value R is 0.0821 when pressure's in ATM. Now, we have different values for R for different units of pressure. Again, not something to worry about here. I just want to make sure that you can see how the math operates here. So given three of these four variables and the constant value for R, we can algebraically solve for whatever we're trying to figure out. Let's take a look at our sample problem. So here it says determine the volume of CO present at a pressure of 0.992 atm at 65 degrees Celsius and with 1.52 moles of gas. So we'll plug those numbers in. We'll do this first one together, and then I'll give you an opportunity to do the next one on your own. So give me a second to get into drawing mode. So the standard form of this that I want you to use is going to be written up here, which is PV equals nRT. Now again, I just rearranged the letters of the formula that we looked at previously, but again, if I look at what we're given here, so we're trying to determine the volume, so we're solving for V, we're given a pressure, a temperature, and moles. Remember that R is a constant value. It's 0.0821. Okay, I'm not, like I said, not too concerned in the units on that, just take my word, it works, I promise. Okay, so we plug this in, so 0.992, so P, V is unknown, N, 1.52, R, 0.0821. Remember, temperature still needs to be in Kelvin here, so that is 338. And then we just rearrange this equation to solve for volume, so divide by 0.992 on both sides. So we plug this in. And what I get is a volume, 3 sig figs, now 2 sig figs for the 65, so it should be 43 liters, should be my volume. Okay. Again, not really one that you can go through and check here as well, but again, I want you to notice how I just simply plug those in and solve. Now, it's not always going to be that easy, per se. We can make these a little more complicated, which is what I have here. So here it says determine the mass of CO2. We're given a pressure, a volume, and a temperature. Okay? I want you to really think about this. Volume has to be in liters. Temperature needs to be in Kelvin. And we can't solve for mass in this problem, but what we can do is solve for moles. So keep in mind how you convert moles to grams. You need to think about that information, all right? I'll give you a moment, and then I'll walk you through it step by step. So we're going to use the same formula here. PV equals nRT. Our pressure is 0.988. Our volume is 345 milliliters. That needs to get converted to liters, which is 0.345. N is our unknown. Our R, same as always, 0.0821. And our temperature, leave a lot of room here, my own bad, 298 Kelvin. All right? So we have all of the variables that are here. Yeah, you just put the equal sign in there, Joe. So we can algebraically solve for this. So we're going to take these values and divide by 0.0821 times 298. And what I'm going to get is the value for N in moles. So 0.988 times 0.345. Divide that by 0.0821 by 298. And what I end up with here is 0.014 moles of CO2. Okay, now the question is not asking for moles, though. It is asking for mass. So we need to do a little bit more with this. So 0.014 moles of CO2. Remember, we can do grams to moles by looking up the molar mass that's found on the periodic table. So we're going to take this value here, multiply by 44.01, and what I get is 0.61 grams of CO2. All right, so we are going to be combining some of the things that we've learned previously when we go through and solve for some of these ideal gas style problems, all right? So we'll do some more practice with this in class, but again, make sure you've got the basics down before we move on to anything more complicated. So the very last thing that we are going to look at today is Dalton's law of partial pressures, and rarely do gases exist as just one gas in a container or in nature, right? Mixtures of gases are common. Consider air, which is a mixture of nitrogen, oxygen, carbon dioxide, a little bit of argon, a little bit of water vapor, that type of thing. This statement is going to be kind of obvious here, but the total pressure of a gas is directly correlated to the individual pressures of a gas added together. So, for example, we've got gas A at 1 atm, gas B at 3 atm, and gas C at 2 atm. Well, if I combine all of those together in the same container, provided that the volume of the container does not change, then the pressure is additive, which means that the total pressure is going to be 6 atm. So the total pressure is equal to the individual pressures that are added together. I promise you, it's not meant to be rocket science, all right? We'll do one more practice problem, review our laws for gases, and be done for the course. So as always, just make sure you read the questions very carefully. It says the total pressure exerted by 3 gases is 742. So that is going to be the total pressure, or P tot. The partial pressures of nitrogen and oxygen are 581 and 143. It wants to know what the partial pressure of water is in the substance. So remember that the total pressure is going to equal the 3 individual pressures that are added together. So P1 plus P2 plus P3. So this is very, very easy to do. We're going to take the total pressure, 742, individual pressures of 581 plus 143 plus our unknown partial pressure of the water. So take 742, subtract 581, and subtract 143, and we end up with a partial pressure, P3, of 18. Make sure you include a unit with that, just like you do with everything. Okay? So again, pretty straightforward to do that. Just make sure you understand what you're trying to solve for, and you will do just fine on all of these, all right? Let's get on. And so really here is just a review of the gas laws that we've gone through and covered. So like I said, I don't want to spend a lot of time on this because it's not as important as some of the other things that we've addressed. So if we've got time at the end of the semester, this is kind of what we're going to be going through and taking a look at. And I'll probably flesh this out a little bit in class, but that gives you a review of all of the gas laws. Again, thank you so much for all of your help this semester. I appreciate your time. If you found that useful, feel free to like, subscribe, do what you got to do. Best of luck to you in the future. And who knows, maybe we'll cross paths sometime soon. Bye, everybody.